Hi, this is Paul Schreiber, and thanks for coming to our third and last installment on the Alesis Midiverb. This goes over the software and DSP architecture. It's a series of PowerPoint slides prepared by my DSP partner, Eric Brombaugh. I'm not as good in DSP as he is by a long shot, so I'm just going to present his material for him, and I hope I can do my best. At the end, there'll be some articles that you can look up on the web that can explain this in greater detail. As a recap from our series last time on the schematics, the Midiverb designed in 1985 came out in 86, designed with off-the-shelf LSTTL and the new HC logic. There's no custom chips. Those were introduced in the Midiverb 2. There's standard dynamic RAM, set up as 16K by 16 buffer, couple of EPROMs, an 8031 microcontroller, a 12-bit DAC, and a 12-bit successive approximation register to do the ADC conversion, and standard TLO72/082 op amps and an LM311 comparator. Again, everything strictly off the shelf. Here's a block diagram of the hardware itself. Again, we went over this a little bit in the schematic. It takes MIDI in through an interrupt line on the UART and scans the buttons and the 7-segment displays. The microcontroller does not have any interaction with the DSP at all, except for giving it the top bits of the address to decode which block is in the EPROM, which is one of the 63 algorithms. The DSP itself is done with discrete TTL logic, and it has an automatic refresh operation for the DRAM, and it has an address calculator, which is a little ALU by itself to calculate offsets into the DRAM for pointers. There's some hardware decoding and some timing software to drive the successive approximation register or the DAC as input side or output side. The stereo in signal is summed to a single signal, goes through a 6-order low-pass filter with preemphasis through the sample and hold. On the output side, there's a pair of sample and holds with some simple low-pass filters. This is the wet-dry potentiometer to a stereo out. It's not true stereo out, and we'll talk about why it's not true. It's actually a pseudo-stereo output. The 8031 is a very simple program. It only uses about 7% of the EPROM storage. It's just scanning the front panel switches, looking for a UART, and outputs the upper 6 bits of the program counter for the block of the microcode. The lower address lines are run through a counter. Basic timing, as we discussed, is a 6 megahertz clock. It uses a ceramic resonator and not a crystal, so it's not perfectly accurate. We're going to assume that it is for this discussion. So it has an 8-bit counter, so it counts from 0 to 255 and rolls over. There's no jumping or execution out of order. This means it has a sample rate of 23.4 kilosamples per second. The DSP runs at half of the clock rate, so it's actually running fairly fast at 3 million instructions per second. Opcode word is 16 bits wide, which requires a double fetch from the 8-bit wide EPROM. The first byte fetched is the 8-bit row, and the second byte is the 16-bit column, the 2-bit opcode. The reason we refer to these addresses as rows and columns is that's how the DRAM associates it with the multiplexed pins on the part, and we have to go through all the row addresses in the refresh time. The DSP accumulator is clocked at every instruction. DRAM reads or writes at every instruction. Since it's a double fetch, 256 bytes, 128 words, so you have 128 instructions to execute every algorithm, and 3 of those instructions are at fixed addresses, and we'll talk about that. Again, mono input, stereo output. Here is Eric's SPICE program where he simulates the input filter. I did this on mine, but he added the phase of the filter, this dotted line below. You can see the peaking here right around 10 kilohertz. That's the preemphasis as a treble boost done on purpose so that when the output filters roll off, it tends to be a little bit flatter here. This was introduced in cassette tapes. The output filter is fairly straightforward. It's actually a Chebyshev. There's just a little bit of ripple here. The reason you want a Chebyshev and not a Butterworth is that the initial slope is a little bit steeper at the cost of ripple. He's just trying to get the last little bit of high frequency response right there. This is the phase shift. The phase shift is actually quite smooth, which means it'll have a little bit of overshoot, but not very much for square waves. Let's talk about the instruction. So if you actually look at the code in the EEPROM, it takes 2 bytes to get the instruction word. You have 2 bits of operation, so there's 4 operations it can do. 14-bit of an address offset, so 14 bits means we can address 16K. Offset we'll talk about, that's how you address pointers into the buffer. It's low Indian byte addressed, so the first bits are the rows, 6 bits are the columns, the 2-bit operation. And it's 1 stage of pipelining, which means that the operation bits lead the address bits by 1 cycle, and we're going to talk about that. So when you actually look at the disassembled code, when you see an address instruction, you have to understand that's for the following operation and not the existing operation. That's to allow the TTL logic to actually do the add 1 clock cycle before the next instruction. So here is a detailed block diagram of the actual DSP engine. So we're going to start over here on the right side. As we talked about before, the basic DSP instruction is called a multiply accumulate. But since we don't have a hardware multiplier, we do successive add and accumulates. The adds are done with physical 74LS283 adders. The accumulators are latches, and then we have 2 output latches called R0 and R1. The difference is one is inverting and one's not inverting. That's why we have this little bubble here. That's so we can do 2 complements for negative numbers if we need to. We have a fixed input gain of a half here, which is divide by 2. And this is done so he can make the math easier. It's arbitrary, and we'll talk about why he picked that. Just because it's easy to do is one reason, because it's just a simple shift by 1 bit. You have a 16-bit wide data bus, even though the data that comes in is, quote, 12 or 13 bits. We'll talk about what we mean by quote in a minute. And so this has what we call 3 bits of guard band. So a guard band means that when we do these operations where we're doing the calculations through here, that we can overflow or underflow by a factor of 8 from the original input data. When we actually have some saturation logic as well, you see down here it says saturation, we can calculate if we're going to overflow the accumulator. So let's talk about these 4 exciting opcodes. And so how can only 4 instructions make all these wonderful reverb effects? So what are the 4 instructions? We just know that there's 2 bits, so there's 4 instructions. And so what Eric did was he said, well, I'm just going to make up my own mnemonics based on the function. So in this chart, you have the operate, you have these 4 lines. These are actually TTL control signals in the hardware. And what we did to figure out what the operands were, we looked and see what these signals actually did in the hardware first and worked our way backwards. So the first operand we're called a sum by half. So with the opcode is 0, 0, all these lines are high, which means that the accumulator takes the contents and adds whatever the address is pointing to by half and adds it together and does a sign extend if you need it. If you look, there's nothing, quote, external. When you do a multiply, you have to do successive adds. So in the code, you're going to see a lot of this instruction that goes out and fetches the data and puts it into the accumulator. The next opcode is 01. What this does is that it simply takes the DRAM address and divides it by 2 and does a load. So this is called load by half. This is usually the first instruction that you do, so you have to get data from somewhere. The algorithms have a lot of the following. First you'll see a load accumulator, then you'll do multiple copies of this where it simply adds over and over and over again to do a quote multiply, and then when it's finished it saves it, and this is called the store. We call it store positive and store negative, and the difference is whether you write to register R0 or R1, because one of them has that inverted output and one does not. These 4 instructions done over and over again in the right order with the right pointers to the memory is what makes a reverb come out. Doesn't seem like much, does it? Let's go find out some more. So the first thing we noticed that in Keith Bar, let's make it as cheap as absolutely possible. You should have worked at Tandy at some point. There's no hard reset. In other words, when the DSP powers up, we don't have any idea what it's doing. And so it just starts running an arbitrary address somewhere in the middle of the program, which means that when you first turn it on, you're going to get a little noise burst. Also, we found out that there's no hardware muting, so that when you change programs, like say going from 11 to 12, it just simply points immediately to the next program block and starts running the code, has no idea what the last instruction was and doesn't care, and it does not flush the audio buffer. For the first couple of cycles through, you have some kind of weird mixture between what you had before and what's coming out now. So maybe that's part of its charm, I don't know. There's no branching, so you have a fixed deterministic execution path from beginning to end. The hardware then rolls over itself, and it just keeps doing that forever until you change the program. The one thing that's kind of unusual about this DSP is how it does memory addressing and how it does address decoding. So instead of having some fixed ports to read and write things, they're memory mapped inside of the program memory. So there's not a separate map for program memory and IO memory. It's all in program memory. So we have 3 fixed addresses in every block. So think of this as an offset. So the very first instruction of any algorithm is read the data from the SAR, which kind of makes sense, right? At address 00, the hardware decodes this, it puts it into the SAR mode, it waits and it runs, and when the SAR is finished, it goes and gets the data. The other fixed address is at address 60 hex, which is right to the DAC write channel. So that means between address 0, which is a read, starting from address 1, and then going to address 5F in hex. That's how many instructions. Remember, it's 2 bytes per instruction. That's how many instructions you have until as soon as you get to this address. Remember, you can't jump over it. When you get to this address, whatever is in the accumulator, boom, it's going to go right out to the right side of the channel DAC. And then you have another 16 addresses here, right? And 16 addresses is 8 instructions. And so you have 8 more instructions, and then boom, out goes the left channel. So the A to D and D to interface are kind of wacky in the sense that Keith Bar tried to get one more bit out of there. He just decided he was going to try to get a 13-bit signal to noise ratio any way he could. For the input side, he's going to hardware have 12 bits coming in. Can't do that. So he does a left shift bit and a sign extend to 16 bits. Now that's really not getting any more resolution or accuracy, but he just did that anyway to get 1 extra bit. That's not going to do all that much really. What he kind of gains is something on the output side, and this is done with hardware. And when I did this reverse engineering and I drew this, I thought I was losing my mind. For one thing, it was a 10 meg ohm resistor, which I'm always suspicious of anytime I see a 10 meg ohm resistor. It's so high value, it's almost like not having a resistor at all. I'm like, what are they doing with this 10 meg ohm resistor? And it's going to the output of an HC buffer, and then the other side of the resistor is going to the current input of one of the DAC outputs. We call this yanking, and so what happens is every so often when he wants to generate an extra 1 in the 13th bit position, he pulls on that part, and that makes the output of the DAC go up a tiny little half step from the other bit, and he kind of calls that 13 bits. So when does he decide when to yank it? Well, he has a little bit of logic in the schematic. You can trace that back and see that he looks and see what the top 8 bits are. So now let's talk about how we're actually putting addresses into the DRAM. This is all done in hardware, by the way. Okay, so we don't have a software calculator for this. This is done in hardware. So what we do is in the microcode, we have a 14-bit offset that's split into rows and columns. This is, again, nomenclature for the DRAM rows and columns, RAS and CAS signals. And there's an adder in here so that the microcode puts an offset in, and this offset is added every time. So if you put a 15 in here, it's going to count every 15 addresses. Boom, 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 boom. And so it's going to go through the memory in this step, because remember, it takes the output here and adds it back, and this is fixed. What happens is, this is how you do pointers in memory, because you have multiple offsets, and the pointers, if you calculate the values right, they'll never cross each other, because they're always going to increment through the counter by 1, but then they're added by the offset. So the pointers go through the memory in steps of 1, but they're all offset from each other. So again, here's a little bit more about the address calculation. This chart down here shows how the addresses are stored in the opcode. First fetch are the lower 8 bits. We call that the row. The next fetch are the upper bits plus the 2 bits to decode the opcode. The address offsets in a program have to sum up to a value that walks through the total number of RAM locations in the buffer, modulo 16. And what happens is, if you look at the code, that when you get to the end, you have to adjust because the contents are off than when you started. And so there's a little adjustment to make sure that you don't go over the modulo 16. So let's talk about how do we program these algorithms. There was a lot of papers written, starting with a guy named M.R. Schroeder, about guessing what the best way to do reverbs were. And this was all done with delays and filters and speculation. It was hard to do the hardware. This is all mathematics. I've got some links to another paper by Andy Moore about that. But essentially what they found out, strictly by trial and error, was that it's a combination of all-pass filters and time delays. The first thing we have to do is we have to multiply by coefficients. And the coefficients can either be positive or negative, greater than 1 or less than 1. In our system, since we don't have a multiplier again, we have to have repeated instructions to ramp up or down to the value that we want. The next thing is an all-pass filter. This is the most important thing in making good sounding reverbs, is how do you have an all-pass filter? A lot of people are saying, what the heck is an all-pass filter? If it's an all-pass filter, that's a wire. Well, the answer is, yes, you're right. The frequency response is a wire, but not the phase response. Some operations require what we call a dummy address to put data that won't actually be used. And so look at your offsets, right? If you can overflow it, it'll wrap the DRAM addresses to usually low numbers like 2 or 3 or 4. And he uses that as a temporary register, like a scratch pad memory. And so he never puts an offset starting in a low number, because he knows that at the end, when he does the modulo arithmetic, he's going to be off by a few things. So he has his own little scratch pad memory in the DRAM. That's something that's also fairly clever to do. And that's just by picking your offsets and knowing that at the very end it's going to overflow, but that's okay, because right before it overflows, you store it. You cannot alter the DSP characteristics in real time, which means that since this is not in RAM, it's in EEPROM, we can't change the coefficients on the fly. Why would you want to change the coefficients on the fly? Well, that's how Lexicon and Eventide found out they can make really naturally sounding reverbs, is they modulate the coefficients, usually with like heavily low past white noise or pink noise or sometimes some LFOs, so that every time you go through the buffer, it's not exactly the exact same coefficients. The Midiverb 2 can do this modulation, but not the Midiverb 1. So now let's talk about the nitty-gritty of actually making some reverb algorithms. The first thing we're going to talk about is how to multiply something by a constant greater than 1. This is a snippet of code out of some random algorithm. This code is Eric's own version from the binary code over here to actually mnemonics. In our example, we're going to start with the program counter. When we say OE, this is in the block starting at OE. We don't worry about the upper address lines. That's just the algorithm. Like again, we start at 0, but this is just a snippet that we found that does a multiply by a constant. The first thing we're going to do is we're going to use the load half from address 2173, that's in hex. See this offset? So when you see an offset, remember it's not for this instruction, it's for the next instruction. It goes to 2173 and gets the data, and it divides it by 2, and that's in the accumulator. In this example, we want to multiply by 2.53125. And I'll talk about what's special about that number in a second. That number is picked from a list. So in order to get there, we do 1, 2, 3, 4 duplicate instructions, which is we call store positive, and which means it takes the accumulator and adds it to itself divided by half. It does 1, 2, 3, 4. And if you look over here, we started at the value of being a half. So when we do it a half and we add it again, we get 0.75, right? Which is 0.5 plus 0.25. We get this. We add it to itself plus a half again, to itself plus a half again, to itself plus a half again. And then we get this final result. Notice that the opcode now has another pointer to the next offset, but that's for the instruction that's not shown here. Now, if you look at this, you find out, well, there is no opcode that tells me what the coefficient is. In other words, if you look at every other DSP chip in the world, it'll say something like multiply the accumulator times this floating point value. It can be any number. But here, we have to pick between 0.5, 0.75, these. We can't pick in between. There's no way to pick in between because all we can do is take what was there and add it to half of what was there the next time and the next time. So there's a definite table of things that we can pick. What happens if we want to do something and it's not in that table? Can we go in between? The answer is sure. And this is a little explanation how to go in between. Like let's say we want to multiply something by the square root of 2. That's fairly common, by the way. What we can do is we can take this result here, this 1.6875, and multiply it by a number less than 1, and then come back and add it to again. So we can go back and forth between less than 1 and greater than 1 to get closer. And we looked at the code, and we didn't see any place where Keith Barr actually did this. So what this means, if we look at this table and the next one on the next page, he just had a list of coefficients, and he just picked those. And as we say, it's close enough for rock. So when we multiply less than 1, what coefficients can we have? So we can play a little bit. So when you multiply it with less than 1, you have to do 2's complement. That's why we have store negatives here. So again, the mnemonic is you read from this 3712, which just happened to be where it was before, a store negative, another store negative. So once we do that, we can figure out how to multiply that simply again. You'll see that a lot in feedbacks. We'll talk about that at the very end. The most important thing, again, the Allpass filter. So what is an Allpass filter? It's a phase shifter at a certain frequency. So it has essentially a flat response. It's a wire, but it's a phase shifty wire. So this is an example of an analog Allpass filter with a quote, center frequency. We don't say cutoff frequency. We say center frequency like a bandpass filter of 1 kilohertz. And so what that means is at 1 kilohertz, we have a 90-degree phase shift. So if signals less than the center frequency, it slowly goes from no phase shift to 90. Then after that, when you go upper, it goes towards 180, which is, of course, signal inversion. Now, in a digital all-pass filter, what happens is that the inversion point of -180 is half of the sample rate. So that's fixed. So for us, it's half of that 23.4 kilohertz. When we move the center point back and forth and back and forth, it's going to change the shape of this curve slightly. The way that we tell the software where we want to put this center frequency, that's the sample rate divided by the number of delay stages. And so that tells you what the frequency is. So what does an all-pass filter do? It's used to what we call diffusion. So if you have an E520, you have those diffusion controls. Some people call it smearing. You put a lot of these all-pass filters, and in some large hall reverbs, I've seen as many as 60 or 70 individual all-pass filters that smear the phase of different frequencies to simulate different travel times and bouncing off different materials and things like that. So this is the format of an all-pass filter stage. You have an input summer, an output summer, and Z. And Z means a time delay. The Z has what we call feed forward and feedback. So it takes the output, the delay, and it multiplies it by a negative 0.5. That's a negative sign there, but it's important. So you have negative feedback. And then it feeds forward around the delay by a half. So if audio, so think of it, this is an audio sample comes in at every clock. The audio sample, we'll call it the wet signal, goes through this delay and feeds back, and the dry signal goes straight to the summer output. So it has a combination of wet and dry, and in this particular architecture we have an inversion at the end. Now, this is normally shown as Z, and you may see nomenclature Z to the minus number, like Z to the minus 50 or something. What does that mean? That means that delay line is 50 clocks long, 50 sample clocks long. In an RC filter, now we can set the corner frequencies of our low-pass filters by changing the R's and changes the C's, and that changes our filters. In sampled systems like this, what do? Well, we take the sample rate, which is fixed, and we alter the length of the delay line, and that's how we change our filter responses. In our case, how do we set the point? This code here sets 200 hertz. So how do we get this to be a 200 hertz all-pass filter? You take the sample rate, which is 23,400, and you divide it by 200 hertz, and you get 117 samples. Every DSP system, based on the sample rate, will have a different coefficient to set these frequencies. And in our Midiverb, the magic frequency is 23,400. So if you want a 100 hertz or a 50 hertz or a 10 kilohertz filter, that's what you do, is you put that in. Notice that the higher in frequency you want to go, the more granular it is. And most of the filters that are used in the Midiverb are all less than 1 kilohertz. Let's just look at the instructions to do an all-pass stage. We're going to start again with sum half. That's usually always the first instruction, which means we have to load the accumulator, do a store negative right here, and that does the negative feedback. Notice that when we store the negative, it automatically puts the half in there. Then we're going to do a sum half for this stage again, and then another sum half read to do the final one. And notice that the addresses here are all the same addresses. There's no offset right there. So it's putting it there. So how does it get how many stages? You look right here at this instruction and this instruction. So the difference between those are 117 steps. So you're saying, well, where is 3A9F? I don't see 3A9F anywhere. Okay, remember it's one behind, so it's going to be in the instruction up here. Sorry, I didn't put that in there. Here's the 2A2 right here. So that's our 117. So again, that's going to be a 200 hertz point of 9-degree phase shift, which is our sample rate divided by 117. It's exactly 200, by the way. And so we're going to talk about program 22, which is a little reverb at the end. It has 9 Allpass filters in there. And again, when you look at the actual code at the address offsets, all right, because remember, the length of it is, we go from this address to that address. And so that address length is the number of samples. And it turns out it has diffusers from 18 hertz to about 300 hertz. And this is because it's a dark reverb. So it's purposely diffusing the low frequencies. Low pass filters are usually used in feedback systems. Low pass filter is very simple. It's the simplest structure. It's what's the first thing you learn to do in DSP is to go from 1/2 pi RC to a feedback with the summer on the input. And so here we have it. We also have a fixed gain here of 1/2. This is to keep the overflowing to a minimum. And it simply takes the input, divides it by 1/2, and then it adds it to the current sample delay also by 1/2. How do you set the corner frequency again? Well, it's the number of delay stages and the sample rate. So if you have a delay of 1, in this example here that we found between the two addresses, 2171 and 2170, that has a 1 delay. So you take the sample rate, and that's half of the sample rate, and it becomes 12 kilohertz. Well, let's look at what algorithm 22 is. And so here's the full block diagram of algorithm 22. So algorithm 22 is a small dark reverb with a 1.6 second tail. So how is this done? Well, the first question is, how did Keith Barr decide that this whole page here is a proper way to do a nice sounding small dark reverb with 1.6 second tail? The answer is, you probably studied it for 2 years, and you try a lot of things, you read a lot of papers, and you simply try it and see. I know that sounds kind of flippant, but that's the honest truth, is that a lot of this stuff is 100% what we call empirical. You just try it and see. And that's what we can do by looking at the Midiverb code, is we can get these algorithms out. And this particular flowchart is used for a lot of the reverb in there, which means all that he does is he doesn't change the algorithm, he just changes the coefficients. So let's look at a small dark reverb with a 1.6 second tail. Summed audio input goes through a low pass filter and a gain stage, and he drops the gain down. So when he does the math, he tries not to overflow. And it goes through 6 all-pass filters. And each one of these all-pass filters has a different cutoff frequency, or we call it a center frequency. And this was all done empirically. And these range around, in this particular stage right here, I believe they go from about 60 hertz up to about 200 hertz. These all-pass diffusers are fed here. So you can think of this output right here as having the original signal that's smeared in phase across a wide spectrum, and it's added to a series of 3 delay lines with their own all-pass filter diffusers. We call this a tank, and a tank is like a reverb tank with springs in it. So this is actually doing the main quote reverb effect, which is the decaying tail. How do you set 1.6 seconds? It's a combination of what is the gain of the low pass filter here, all right, and the coefficients in these delay lines. So the main tank is copies of the following: a delay with 2 taps on it, a gain stage, again, to try to keep overflow down to a minimum, followed by an all-pass filter. And then repeat it again, and again, and one more little all-pass filter here for good luck. And that sum is fed to a low-pass filter. So this is fixed in frequency, and that's what he calls dark. So you'll see dark, warm, and bright. And the difference is, what is the value of that low-pass filter cutoff frequency? So why do these delays have 2 taps? Well, that's how he's getting his fake stereo left and right out. You can see that the left output is actually the sum of three different things. These three delays summed at, quote, the end of the delay line, and the right, remember the right comes out first, it comes out before the delay line. Now, you could argue, well, you could probably pick these points pretty much anywhere. It doesn't have to come out of the delay line. What if they come out of the diffuser? Or maybe one of them comes up here. Or why here? Why not some here? And I'm sure that he tried all those things. And he found out that this sounded the best. Again, it's kind of a hand-waving cavalier answer, but welcome to the world of reverb algorithms. All these functions are generally groups of 4 instructions repeated like before. So all of our all-pass filters, here, 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 for example, it's just going to be a set of these 4 instructions. That low-pass filter is going to be these 4 instructions. So if we go back and look, how many instructions do we have? We have, let's talk about blocks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 blocks of 4, 48 instructions to do that. And then to pick these points up, remember those are different addresses coded. You have 8 instructions between here and here. And so that's why you can do a lot in a small code space, because each one of these functions only takes 4 lines of code. Well, I hope you enjoyed this talk about the software inside the Midiverb. I know I did a lot of hand waving in some places because to get really into great detail, you need to do a lot of reading. So here you go. For more information, I suggest looking at these papers. The place that you can get the most instruction for free on the internet is from a professor called Julius O. Smith. He's at Stanford, and he has this website. It's called Physical Audio Signal Processing. It's like 200 pages long or something. He basically starts off with, this is a signal, and how do we do everything in music, instruments, and audio. I highly suggest reading it. Yes, it can have graduate level calculus in it, but there's no single place you can go to get the most information. When Keith Barr left Alesis, he formed a company called Spin Semiconductor, and this was to make a custom chip that's even more complicated but less pin count than the chips he did in like the Midiverb 2 and then in the Quadraverb and things like that. And this is called the Spin FV1. It's still widely used today. It's probably in thousands and thousands of guitar pedals and Eurorack, say like the tip-top ZDSP uses a spin part, and the new FX8 also uses a spin part. He has a whole section called a knowledge base on the Spin website that talks about how the spin part does these effects, and you'll notice that it's very similar to how the Midiverb does the effects. So I suggest reading that. When Keith Barr passed away a few years ago, Sean Costello, who wrote the Valhalla, Halls of Valhalla DSP card for the ZDSP, has a really nice interview he did with Keith Barr, and he actually got Keith Barr to talk a lot about the architecture of the Midiverb. And so if you read this interview and go back and look at the schematics and what I just talked about, you'll see that he dropped a lot of hints on how this was done. So this interview was actually very helpful to us understanding how the Midiverb worked. And I kind of put this last one on this side. It's a kind of an infamous paper in the world of the Audio Engineering Society. So there was another researcher at CCRMA called Andy Moore. And Andy Moore wrote a paper where he talked about, it's called About This Reverberation Business, where he did a lot of analysis. And this, I think, paper was written in 78, 79 timeframe. It's published in 79, but I think it was mainly written in 78. He talked about sort of the state of the art of reverb in 1978. So this is before the Alesis Midiverb came out. So now we're talking early lexicon stuff. And he basically spilt a lot of the secrets that Lexicon didn't want to be told And then at the end of the paper, in the conclusion, you have to read it. He basically says, and my conclusion is, all this stuff sounds awful. So it's kind of interesting to read. It is extremely heavy in the math. It's pretty long. It's like a 30-page paper. At the time it was written, there was a gasp in the air when it was published because nobody had ever seen this much data all in one place about DSP and Reverb. Again, thanks for being a Patreon, and I hope to see you again in the future.